Have you ever stopped to think about how much actual work you can get out of a system? I'm not talking about the total energy it's holding, but the useful get things done kind of energy. Well, that's exactly what we're going to break down today with a really cool concept from thermodynamics, Helmholtz free energy. So, here's our game plan. We'll kick things off with this whole idea of free energy. Then we'll pin down what Helmholtz energy is specifically. After that, we'll decode its famous equation, see where it pops up in the real world, and finally put it head-to-head with its more famous cousin, Gibbs free energy. Let's jump in. All right, first things first. What do we even mean when we say energy is free? It's a really important distinction because, as you're about to find out, not every bit of energy packed into a system is actually available for us to use. So let me just ask you this straight up. If you have a system that's just full of energy, can you convert 100% of that into useful work? The short answer is nope. A certain amount of it is always, well, unavailable. And that's where this next idea becomes so important. The proper scientific term for this available, useful energy is thermodynamic potential. It sounds a little fancy, I know, but just think of it as a system's true work-producing power. It's the concept that tells us how much bang for our buck we can really get from the energy inside. Okay, so let's get specific. There are a few different types of thermodynamic potentials out there. The one we're zeroing in on, Helmholtz free energy, plays by a very specific and important rule. It's all about systems where the temperature and, this is the key part, the volume are held constant. And here it is, the formal definition. Helmholtz free energy, which we represent with the letter F, is the absolute maximum amount of work you can squeeze out of a closed system. But, and this is a big but, it only works under those super strict conditions. Temperature isn't changing, and the volume is totally locked in place. All right, let's talk about this equation. Now I know F equals U minus TS might look a little intimidating at first glance, but trust me, when you break it down, it reveals a really simple and honestly beautiful idea. It's going to make perfect sense. First up, we've got U. This is just the total internal energy of the system. Think of it as your starting budget, every single bit of energy that's in there. It's the kinetic energy from particles whizzing around, the potential energy in their bonds. It's the whole pie. Now for the really interesting part, the piece we subtract, TS. T is just temperature, and S is entropy. You've probably heard of it. It's basically a measure of randomness or disorder in the system. So when you multiply them, this TS term represents the amount of energy that's just lost to chaos. You can't use it, you can't organize it. It's the energy tax you have to pay to the universe's tendency towards disorder. And this brings it all together perfectly. The equation F equals U minus TS is really just saying that your useful free energy, that's F, is what you get when you take your total energy U and subtract that unavoidable chaos tax, TS. It's literally what's left over for you to actually do something with. And, this simple-looking equation wasn't just pulled out of thin air. It's derived directly from the first law of thermodynamics, the fundamental rule that says energy can't be created or destroyed. Scientists start with that law, apply it to a closed system, plug in the definitions for heat and work, and after a bit of rearranging, out pops the Helmholtz function, F. That solid mathematical foundation is why it's such a powerful tool. So this might all seem a little abstract, but I promise you, Helmholtz energy is a real workhorse in some very modern fields. Let's take a look at how this principle is actually being applied, everywhere from giant industrial machines to artificial intelligence. Here are two awesome examples. In engineering, the Helmholtz function is absolutely essential for creating super precise models of fluids, like the industrial refrigerants that keep massive data centers from overheating. And then, get this, over in the world of AI, it's used in a type of neural network called an autoencoder to help it figure out how to efficiently compress data, like an image, and then reconstruct it. Pretty wild, right? Okay, for our final section, we're going to do a little showdown. We're putting Helmholtz side by side with its more famous counterpart, Gibbs free energy. Comparing the two is probably the best way to really understand the very specific and unique job that Helmholtz energy does. At first glance, their definitions look pretty similar. Helmholtz measures the useful work, while Gibbs measures the maximum reversible work. It's a subtle but important difference, but the real key, the thing that separates them, is the conditions where you use them. And boom, here it is. This slide is the whole story. They both work at a constant temperature. But Helmholtz is your go-to tool when the volume is constant, while Gibbs is what you use when the pressure is constant. This one little difference, it changes everything. So you might be wondering, okay, why do I hear about Gibbs all the time, but maybe not so much about Helmholtz?
Well, it's because most chemical reactions we do, whether it's in a lab or in a giant factory, happen in containers that are open to the atmosphere. That means they happen at a constant, stable pressure. And because of that, Gibbs-free energy is the right tool for the job well over 90% of the time.
Here's the absolute perfect way to picture it. Imagine a chemical reaction happening in an open glass beaker on a lab bench. The air pressure on it is constant, right? That's Gibbs territory. Now, imagine a reaction happening inside a sealed, super rigid steel container, like a bomb calorimeter, where the volume physically cannot change. That is the special domain of Helmholtz free energy. And that leaves us with one last big idea to chew on. We know what to do when volume is constant, we use Helmholtz. We know what to do when pressure is constant, we use Gibbs. But what about a dynamic system where both are changing all at once, like in our atmosphere or inside a star? Well, that's a doorway to even deeper, more complex ideas in thermodynamics. It's a great reminder that to unlock any system's true potential, you first have to understand the conditions it's playing by. Thanks for watching.